Hi, in this presentation, I'm going to talk about hydraulics and pumps. As you recall, we already had another conversation in part of this course where I talked about hydraulics. So hydraulics in this sense is going to be in reference to talking about types of capacity, the hydraulics of our systems, and then transitioning directly into pumps. So hydraulics is the hydraulic integrity of a water distribution system is defined as its ability to provide reliable water supply at an acceptable level of service. That is, meeting all the demands placed upon the system with provisions for adequate pressure, fire protection, and reliability of uninterrupted supply. This comes from a 1995 AWWA article. So that leads us into our next slide where I'm going to talk about capacity. So according to Safe Drinking Water Act, Part 11, Sub-Rule 5, Number 1, underneath that, distribution systems shall have sufficient capacity to meet peak demands, including fire flow demands, where fire protection is provided, while continuously maintaining a minimum pressure of 35 psi throughout the distribution system under normal operating conditions, and 20 psi throughout the distribution system during emergencies such as firefighting. So that last little bit there also is a little bit of more nuance to that. So if a water system is to provide capacity, that means in a bunch of different fashions. So capacity is meaning you're going to be able to meet the demand of your system regardless of what time, if it's peak demand, low demand, so on and so forth. And capacity can be done in a number of different ways. Capacity can be met by making sure that you have a water plant sufficient enough size to produce water to meet your peak daily day demand along with just your overall capacity. You may have well houses, making sure you have enough wells and enough water from those wells that they're not having and going to be sucking dry and damaging the pumps, but they're also going to be able to provide enough water to meet the capacity and demand of your system. And sometimes it's not just about the source that it's coming from, okay? So sometimes it's making sure that you have adequate water main size, that they are big enough to provide enough water and flow to meet your demands. Another thing is possibly having storage throughout your system. And with storage, that comes with a number of other things. If it's an elevated storage tank, not only is it going to provide water storage to help curve that demand to put less emphasis on having to run those pumps during peak demand system, where maybe you can fill the water tanks during off demand hours like at night, and then during peak demand in like the morning and at night right after school and work, that the reservoirs are used to meet that, to offset the need to have continuous pumping or production at our water plants. Because with peak hours, pumping and operating during peak hours now, we're being charged a premium as a water supplier to run our pumps, to run our system, and so on and so forth. And along with that, not only do water storage sometimes help with meeting our demand flow, but they also help with pressure, because we learned, and the other thing, the higher the water is, the more gravity acts upon it, the more pressure it exerts down into your water mains and provides water and pressure for your distribution system. Along with this, you might have to have booster stations throughout your distribution system to adequately give you enough pressure, especially if you're in an area that has lots of hills. A lot of towns in Michigan have various different pressure districts throughout their town, meaning they have different pressure levels and requirements to provide adequate flow in these areas. Now, the 20 psi under fire emergency, that is actually not to last more than 4 hours at that thing. So another thing about this is a lot of times cities undergo reliability studies. The reliability studies make sure that all those things I just discussed are in place, meaning you have a way to provide adequate capacity to your system through various different means, meaning you have the right size water mains, you have this water storage, you have the capacity at your plant or your well houses, and so on and so forth. And all of these drawings and all these layouts of your system are going to be included in your general plan that we talked about with rules and stuff. So if you remember what hydraulics is the study of liquids at motion and in rest, and water within your distribution system is at motion all the time as it's flowing through your pipes. It's at rest in your storage tanks, and it takes the shape of the containers that it is put into. So it has a weight, it has a density, and water exerts pressure, especially if it's being driven by gravity. All right. So The very first thing, if you remember too, we talked about friction. Friction is the resistance of change in motion, right? Objects, or water included, want to resist motion. But when they are forced to move, there is friction involved. So as water moves through the pipe, it's going to experience friction loss moving through a water main. The rougher the pipe is, the more friction loss we're going to have. And head loss is the amount of height that, well, head in general is the height of water, but head loss is in reference to the loss of vertical distance water can travel due to a conversion of its energy that it's given. And that would be friction. The more friction loss you have, the more head loss you have, all right? And we talked about that in that other section with that example talking about a water treatment plant. Now, the next thing we're going to talk about too is the continuity equation. We also talked about that a little bit, and that's talking about flow through pipes, and it also talks about flow through reduction of pipes. If you go from a 12-inch main to an 8-inch main, it's 300 gallons per minute as the flow in is going to be equal to the flow out. That is another thing to keep in mind when doing this. Part of the presentation, we're going to talk about the various types of pumps, a little bit about history of pumps, some terminology about pumps, and just some general knowledge about the pumps that are used in the water industry. Let's talk about the history of pumps. So pumps, believe it or not, are over 2,000 years old. The first documented pump that we know of is the Archimedes screw pump that was invented 287 BC by Archimedes, who was a Greek inventor, philosopher. So what a pump is essentially is a mechanical device that transports liquids from an area of low pressure to high pressure, one of low elevation to high elevation, or it also moves more water. And you see this in various different things with our high and low service pumps at our plants, your booster stations, or even lift stations for wastewater. The screw pump is still something that, when you hear of lift pumps, is still in use in wastewater, because anything that fits in the void space of it will be pumped. So pumps consist of some sort of impeller, some sort of drive device, and some sort of motor that moves this drive device in order to move the liquids from one area to another. So they're going to be used in various different fashions for filling tanks, adding additional pressure, or just even adding more flow coming out of a well or coming out of a plant. And they're going to be driving into our distribution systems, our reservoirs, or even in booster stations to help just transport and add more pressure to our faraway customers. So there are lots of different pump terms that can be used here. You have suction lift, static discharge, solid dynamic head, prime, impeller, casing, shaft, shaft sleeve, packing, lantern rings, separator rings, packing gland, cavitation, brake horsepower, pump curve, and efficiency. And the thing is you don't need to know all these by exact definition, but you have to have an idea of what they are. So suction head or lift is the vertical distance between the center line of the pump and the free liquid or surface of the liquid or water that is being pumped. Suction lift is lifting it, right? And suction head is feeding down into the pump, but it's from wherever that water line is down. Then you have your static discharge head, which is the vertical distance that a pump after the pump can push the water. All right. Now you have total dynamic head, and total dynamic head is a combination of the total amount of head or vertical space that a pump can move the water, either lifting it or pushing it, or a combination of both. All right. Prime is when a pump casing and the impeller shaft itself is completely full of water, so that when the pump is engaged or turned on, that it is able to suck and pull water through it. Now an impeller, this is a piece of the pump that pushes the liquid and moves in a circular motion using centrifugal force to push water. You have the casing. The casing is what surrounds the impeller and allows the water to be pumped through it. A lot of times, like we're talking well casing, all right? The shaft is the device coming from the motor of the pump that again goes into the impeller, that spins the impeller and makes the water move. And then you have a shaft sleeve, which is part of the shaft. This helps keep it centered, provides lubrication to prevent it from damaging itself or overheating. You have the packing, which is another form of thing around in the stuffing box that provides lubrication, because this is like a graphite impregnated nylon looking rope that provides lubrication to the pump shaft as it spins. A lantern ring serves as the base for the packing itself. Then you have separator rings, which you have the lantern ring that serves as the base where all the packing gland goes in the stuffing box. And then you have separator rings in between each one of the packings or packing glands. Cavitation is the introduction of air into a pump. Cavitation with introduction to the pump can cause damage. Then you have brake horsepower. All right. This is part of a pump efficiency curve. The pump curve helps determine whether the pump we have fits our needs by determining the amount of output based on the amount of energy put into it. And the efficiency at any given output and time for that is known as the pump efficiency. So here's just some pictures of showing what we're looking at here. So here we have suction lift and discharge head. And like I said, the total of these is known as a total dynamic head. So in referring to a pump, if you hear a pump has 200 feet of total dynamic head to it, that means a pump can lift, like in this case, if we say this is 200, let's say it lifts at 100 and discharges at 100. You add those together to get a total dynamic head of 200 for this pump. Suction lift is exactly sucking it up into the pump. Discharged head is the amount of feet of head after the pump can push it, after it's pumped it. Now, suction head is a little bit different. As you can see, suction head here feeds down into the pump. So when it's feeding down into the pump, and this is what you see a lot of with horizontal drive shaft pumps, the suction head is pushing down into the pump, and then it's discharging out. That is all known as discharge head, okay? So there are three main types of pumps that exist. With that, the main other type is known as a jet pump, but we're not really going to talk about that. So we're going to be talking about centrifugal pumps and positive displacement pumps. Your positive displacement pumps are your chemical feed pumps, all right? So we will not discuss jet pumps, which is the third type of pumps here, because jet pumps are not used in municipal fashion. They're used in non-community small installations, and they're used in houses too, because they work where they inject pressure down into the pump casing or well casing, and then it forces water back up. But those are not anything that produce enough water. So centrifugal and positive displacement are the most commonly used pumps in a community water supply. And like I said, positive displacement is a chemical injector pump, where centrifugal are the ones that are used for producing and pushing and sucking up water and discharging it from the treatment plant. So the types of centrifugal pumps, all right, we're going to have a line shaft vertical turbine, a horizontal turbine, and then a submersible vertical turbine pump. All right. Vertical turbines and submersible vertical turbines look identical to one another, just they operate a little bit in different fashion, and they're positioned differently in a well casing used for that. Horizontal turbine pumps are different from that of both of these because they are in a left to right fashion where the motor sits horizontal to that of the impeller. All right. And this is typically that suction head diagram you've seen earlier. That's typical of a horizontal turbine because water feeds down into it. All right. Which we'll talk about that and show examples of that. So one big thing to keep in mind is cavitation. Cavitation sounds like, when it's going through a pump, it sounds like your pump is literally pumping gravel, all right? Make some pinging and some dinging noises and just think about what it would be. So cavitation is the introduction of air, bubbles, or vapor into your impeller casing, okay? So this will cause significant damages to the impeller, as you can see in this picture. It's destroying the fins of the impeller. Well, the fins of the impeller are what cause it to give it force and suction when using your pump. So if you ever cavitate your pump it's going to create vapor lock, vapor bubbles, which will then damage your stuff. It can increase corrosion rates because of the addition of air into that. So these are very bad. The introduction of air bubbles or air into thin cavitation will cause long-term damage to your pumps. So here in this picture, you can see we have the two different styles of turbine pumps. Not a submersible, but you have a horizontal centrifugal pump here on the left, which these are all rated at around 20 mgd. These are at the Saginaw water plant, which is part of a larger contingency system known as the Saginaw Midland Pipeline, which is a pipeline that runs down from Augrey to get all their water from Port Huron. And then here on the right, these are vertical turbine pumps, all right? So the difference between these, so vertical turbine pump, as you can see, the motor's on the top, the shaft and impellers go directly down below. So typically a vertical turbine pump sits on top of the basin that it's pumping from. The impellers are down into the liquid or the clear well that are pumping from it. This specifically is Mount Pleasant. This is their rainy collector well that they have. And as you can see here on the left, I was kind of pointing it out earlier that in a horizontal, typically the water feeds down. And if you look at the windows, you can see that these are down below grade. So that's typical of horizontal turbine pumps, is that the water cascades into them because they often lose prime if not. But these are the two typical types of pumps that you're going to see used for high and low service pumps at water plants, and of varying different sizes. They can produce a ton of water. These can also serve as booster pumps if need be, especially the vertical turbines out in your area, all right? So horizontals have a very much shorter shaft to the left there versus a vertical turbine, which has a longer shaft directly into the clear well itself. So one thing about line shaft vertical turbine pumps is they are common in pumping water in lots of different applications, especially for the fact that the impellers are lowered down into some sort of tank or clear well where these are. The impellers rotate with the shaft. And again, I guess I don't know that I talked about this in here, but you're going to get multi-stage impellers. The more impellers that are on a pump, the more pressure and total head that it pushes. More impellers does not mean more water production on a pump. More pumps means more water production. The stages or impellers of a pump, this goes for any of them, just means that it'll give more pressure to the water and be able to push the water further and give it more head and energy. So how this works is the water comes in down through the screen on the bottom of the shaft here. It comes into the first impeller, then it's fed up and kicked off to the left. And as you can see, there's sort of a void space up here at the top. And that void space at the top is where you're going to find your stuffing box for maintenance on these things, with the packing gland and separator rings and stuff that we talked about earlier. And you have the pump right here on top, the motor's on top. And as you can see, the shaft is centered down, directly down the case from it and into the clear well itself. Horizontal centrifugal pumps, the motor lies horizontally to it. So these a lot of times are high service pumps or booster pumps when priming is not a problem. That's why water needs to be fed down into these, because if they are on the similar level, a lot of times they will cavitate themselves and lose prime. And when a pump loses prime, they're not necessarily going to move water as much. So that's why they have to have suction head, meaning the water cascades down and they're typically below grade for that matter. So some of the disadvantages to it is the lubrication of it. For the fact that the water is held horizontal to it, the motor and pump shaft are directly in line with where the water is. Whereas on a vertical turbine, the water's got to get up there. Well, gravity, if turned off, is not going to allow it to get to it. Whereas water in this, gravity pulling down into it, could pose a problem with getting in there and lubricating the pump shaft and replacing the packing gland and so on and so forth. So lubrication and maintaining prime are the two biggest problems with horizontal.
So the next type of pump we're going to be talking about is submersible pumps. So submersible pumps are a lot like a vertical turbine pump, and they have a lot of similarities in what they look like. But the big difference about a submersible versus a vertical turbine pump is that it is the reverse. The motor is mounted on the bottom of the impellers, and it's also lowered down your well casing and into your well. And on the next slide, you'll see the varying differences between the two, but there's a lot in common that they have. But so with submersible pumps, they're called submersible because, like I was just saying, they're placed on a well casing or they are completely submerged in water. Now, with these, they they have some advantages to them. Some of the advantages is they have no internal valves except the T valve. There's no lubrication needed for the fact that they're lowered into a water column and always in water or some liquid. So there's no need for lubrication. There's typically no need for any type of cooling apparatus because this is in the thing. They have a low initial upstart cost to them, and they require little room in comparison to the capacity amount, and they're practically noiseless for the fact that they are lowered down into these casings. So what's a disadvantage to these? So one thing that needs to be talked about here with a submersible pump, they do make these all the way up to 2,000 horsepower. Another thing about submersible pumps is they have a very short shaft, right? But when these are operated on a VFD, you cannot just turn them down to turn them down because they are operated to have a certain amount of water flow through these. We have what's called a pumping sweet spot. And this even goes for our other pumps that we've talked about. A pumping sweet spot is typically anywhere from 35 to the 85% mark. And that's where we want our pumps to be running because believe it or not, if you turn a VFD down on a submersible and you're like, oh, I need to produce less water, and you turn it down too low, submersibles are designed to have a certain amount of water flow past them as they're in use to allow proper cooling. So if you turn these or throttle them down too much, you could be doing just as much damage to the pump because of overheating due to insufficient water flow past the pump itself than running it at 100% or full bore all the time also. So that's one thing to keep in mind, that there's a pump sweet spot for all pumps, but in submersibles in particular, because the water flow past them is designed to cool them. And I think I'd mentioned this previous, but when you have multi-stage pumps like you do here, the additional stages do not give you extra output. The additional stages on it only give you additional pressure. Output is determined by your bottom impeller. So there's things they can do to adjust the pitch of the fins, the size of the impeller, and size of the gaps, and so on and so forth to increase it. But there's only so much you can do to get so much out of a pump because it's based on the impeller itself. So here, these are the different types of centrifugal pumps, and this is showing you the vertical turbine pump versus a submersible. And you can see that they're very similar in nature. Now the shaft is a lot much shorter than on a submersible, and the motor location is separate. But as you can see, there's a pump intake screen, multiple impellers, and the water is pumped by the impellers moving in an upward motion and pushed or pulled. And so it's very, very similar. The pump shaft now is different. Of course, the submersible is not going to have your stuffing box with packing glands and separator rings and lantern rings, such as that as a submersible. But as you can see, they're very, very similar in nature here. Now, on the next slide here, we're going to talk about impellers. So there are three different types of impellers. You have an open, a semi-open, and then you have your closed. So as you can see, they each kind of have their own functionality, whereas open is used for solids handling. This is what you're going to see in wastewater plants or areas or like sludge pumps and so on and so forth. Semi means that it's dealing with moderate abrasive slurries. You could use this type of thing in pumping cement and stuff along those lines, or just like sludge because it's mixed abrasive. It's not something that's going to have big contents and chunks in it. And closed. So closed ones are for used high head, meaning lots of pressure to push the water, high flow, and improved efficiencies. Because the fact that it's a closed system, it doesn't have any of the efficiencies that you have with the opens where materials there's like void space in there, whereas these do not. Okay. The closed ones are what you're going to see on your high and low service pumps, your submersibles, and so on and so forth. So here's kind of a breakdown of some pump parts, just showing in impellers and casings and horizontal. This is they were replacing the horizontal impeller here. This was done at the Saginaw water plant, is where this at. This is a 33 MGD pump. That pump can produce 33 MGD, which honestly, in this realm of things, that's kind of small fries in comparison to some of much larger plants. So here's again is just showing you how the impeller works. The water enters through the middle of the impeller, and as the impeller spins, it throws it out into the impeller casing. It throws it out in a centrifugal force. It uses circular motion, give the water pressure. So as it spins, it throws the water out and gives it. And like I was saying, additional stages, it moves up to another impeller, which gives it more pressure, goes up to another one, gives it more head and another head. So more multi-stage pumps do not produce more water, they produce more head. All right. Here gives you an idea of what you're looking at vertical turbine pump parts. So with a vertical turbine, you have your motor up top, then you have your packed stuffing box, which we'll talk about more, but that includes like your lantern rings, separator rings, and so on and so forth. Then you have your line shaft, and on your line shaft, you're going to have your shaft coupler and shaft sleeve too down it. And then you see you have your impellers and you have your ball bearings, which are attached. All right, and then you have your screen at the bottom there that brings this all up. All right, and as you can see, this is like a 3-stage pump here. All right, so here on the next page we have the stuffing box. So this entire thing is known as the stuffing box. Okay, at the base of the stuffing box, you're going to have a lantern ring, which serves as the base for all your packing glands and separator rings. Now, a small amount of leakage around the lantern ring is typical. You will have a small amount of leakage, not excessive. Now, if you have excessive leakage coming from the stuffing box and lantern ring, that means that it probably needs to be repacked, where you have to take it apart and repack it with new packing gland and separator rings, okay? So the lantern ring is the basis for the stuffing box and the packing glands. It is very typical for it to leak, like I was saying, because it allows proper cooling. The water is for cooling and lubrication. All right. Now, as it continues, you have your packing gland, which I've described in the past, but the packing gland is it looks like a nylon rope that's impregnated with graphite, right? And it's cut to fit typically. So as you're restuffing the box, you're cutting these glands to fit, putting a separator in, do another one, and there's going to be multiple. Now, you want to make sure after you've repacked a stuffing box that you do not tighten it too tight. There are specifications for how these are supposed to be packed and tightened. If you tighten them too tight, there's a good chance that it will not get that leakage that is necessary. A lot of times when you're in a plant and you're going to see these little channels cut out on the floor. Well, those channels are on purpose because it allows the leakage that's occurring from the pump to go down some drain so that it isn't a slip and fall hazard. All right, these things do wear out. They do need to be replaced. All right, on a horizontal, vertical, or a horizontal drive pump or horizontal centrifugal pump, these are harder to do because water is constantly trying to come in. Whereas in a vertical, if it's not on, you don't have water coming up into the stuffing box itself. And on a submersible, you're not going to have this at all. So the reason, as we call them turbine and centrifugal, is because what happens is the water comes up in the middle, it spins in circular motion and throws the water out and up. And then it continues on to another one. Like I've said multiple times, stages is energy added, not capacity. If you want more capacity, you got to add another pump. Stages will not do it. Now, positive displacement pumps. So there are lots of different positive displacement pumps out there. There's diaphragm, peristaltic, gear, and piston. But the two that we primarily use for positive displacement pumps in our water systems are diaphragm and peristaltic. And these are used for chemical injection. Some of them have self-metering or self-feeding when they're using electropotential measure to adjust their feed rates. Some are manually adjusted after a check. It just kind of depends on what type of system you have. Your larger systems are going to have online SCADA that self-adjusts based on how things are changing, all right? So a lot of these do not have like an internal prime or internal pressure. They are just automatically prime and pressurized the minute that they're energized. Now, diaphragms work in a pushing-pulling motion where they push and pull a orifice of some kind that creates pressure for input on a check valve system on the back of them typically. And now peristaltic has rollers in it, and we will see some different things with that. So many of the older pumps, though, are piston type forms, but like I said, diaphragm and peristaltic are the new common ones that everyone uses. So here's an example of each here in motion. And as you can see with the diaphragm, like I said, there's some sort of orifice or membrane attached to a shaft, and then the amount of liquid that this can push can vary and be adjusted, and it's adjusted by two different ways. You're looking at stroke length and stroke speed. As you increase the stroke length, you increase the amount of feed, and as you increase stroke speed, it makes that membrane or orifice move faster and also increases the feed rate. I will caution you that a lot of these can have a very large amount of pressure on them, peristaltic and diaphragm both. So when you these, to be safe, if you are doing maintenance to them, please do ensure that they are de-energized. Now peristaltic works, as you can see, a little bit different here. A peristaltic has a rubber tube and a set of rollers, and as the tube goes around, or with the rollers, as the rollers hit the tube, that's the certain amount of volume that is allowed through these. That's why these are called positive displacement. They have a particular amount of volume that they move in each action. That's why they're considered positive displacement, and they have no need for gaining prime because they can get prime immediately just upon being activated and energized. So on these peristaltics, sometimes when doing maintenance, you have to replace the rollers and the rubber, but sometimes, a lot of times, just the initial maintenance is replacing just the rubber tubing itself. They have made these so the rubber tubing only fits in a particular area or a particular way, and particular tubings only might match certain peristaltics as they are proprietary. Now, if doing maintenance on a diaphragm pump, when it comes to the rebuild kit, it is very important to replace all the valves and all the O-rings that it comes with it, especially the multi-mix valve on it too, just to ensure that everything is working properly, all right? You do want to use all the O-rings and all the different check valves that it comes with it to ensure that it's all proper. Choosing to ignore one of those gaskets could end up in failure of your stuff, and it could cause harm to someone. All right, with all that, thank you for listening to me in my ramblings. And I hope if you have any questions, please feel free to reach out to me at any time. We are here. If you have any types of questions, reach out, and I'm more than happy to answer them. Thank you, and have a good day.